Hi, everyone. In this video, we will return to an idea we first discussed in Math 5610, the idea of convergence of sequences of functions. We'll begin by reviewing some of the material that we saw in Math 5610 about pointwise and uniform convergence. We'll then extend those definitions based on what we know now about Lebesgue measure and sets of measure zero, and then look at some new modes of convergence that arise out of thinking about more global types of convergence as opposed to the local types of convergence we've looked at previously. So to begin, recall that we say a sequence of functions fn defined on a set D converges pointwise to a function f on D if and only if, for each fixed x value in D, the sequence of constants f sub n of x converges to f of x. Now, of course, we can translate this into sort of epsilon n language, and we would say that for any x and any epsilon greater than 0, there is an n, and again, that n could depend on both x and epsilon, such that whenever little n is greater than capital N, it follows that the difference between f sub n of x and f of x is less than epsilon. So visually, right, we can think about this, right? The key to pointwise convergence is, okay, so let's imagine here I have a limit function f, and I have some sequence of functions which are converging. So maybe like this is f1, and then maybe this is f2, 2, and here is f3. And maybe here is f4, just to give us ourselves a couple of data points. Again, these could be doing all sorts of weird things. F4, right? But the idea of pointwise convergence is you have whatever your domain sort of set is. Let's say it's just an interval here, but you have your set D here, and you pick a particular x value in this set. So let's imagine I picked this x value. Now, if I pick this particular x value, right, then each of these functions, I just take each of the functions f sub n and evaluate them at the point x. Well, those just become a sequence of real numbers. So if I take the function in red here, f1, and evaluate it at x, right, I just get whatever this height is here, right? So this would just be f sub 1 of x, right? So I can think of this on sort of the y-axis as just some real number, right? And then I evaluate f sub 2 at x. Let's see, f sub 2 of x would just be this value. This would be f sub 2 of x. I evaluate f sub 3, right, at x. Give me that value. So over here, here's f3 of x. And then finally, I evaluate my orange function f4 at x. That's going to give me maybe something like this. Here's the value f4 of x. And now what I'm doing is I'm looking at whether or not this sequence of values converges to this value here, and where this value is just f of x. Now, again, I've only drawn out sort of 4 functions here, but the idea is for each fixed x, I fix an x and I go through and I say, is the sequence of values f sub n of x, these are just real numbers, are they converging to f of that x value? And once I know it works at this x value, I can move to a different x and move to a different x. And if it is true that f sub n of x is converging to f of x for each fixed x, then I say that my sequence of functions converges pointwise. So this is, in some ways, it's a very natural, perhaps even the most natural way to think about a sequence of functions converging. So we looked at this in Math 5610. We proved that certain sequences of functions converge pointwise. It's sort of fairly straightforward. You mostly just use facts about convergence of sequences of real numbers because that's really all you're doing if you're proving that something converges pointwise, right? So but again, the key sort of differentiating pointwise from uniform is that for pointwise convergence, how far you need to go out in your sequence of functions to get your function value f sub n of x within epsilon of f of x, it can actually depend on the x value. Okay. On the other hand, when we talked about uniform convergence, right, we said that the sequence of functions f sub n converges uniformly to a function f on D if and only if for any epsilon there is a capital N. Now notice here this N only depends on epsilon and no longer on x. So there exists an N independent of x such that whenever little n is greater than capital N, it follows that I can make this difference less than epsilon. And the key here is that the same n works for every x in your domain. Okay. So you'll recall that we looked at several examples in Math 5610 of sequences of functions that either converged pointwise but not uniformly, or converged both pointwise and uniformly. Now, in just a minute, we're going to look at that sort of the standard example one looks at is f sub n of x is equal to x sub n on 0, 1. This is an example that converges pointwise but not uniformly. So we'll actually revisit this example in just a minute. But again, the key difference here for uniform convergence is that you should be able to make that choice of n independent of what x value you're at. You should be able to pick one n, which only depends on epsilon, that works for every x value. Whereas again, with pointwise convergence, that choice of n could vary as you vary your x values around in your domain. Now, the reason I mentioned that pointwise convergence is maybe the most natural sense. So you might wonder, well, why uniform, right? Well, remember that uniform convergence was sort of one of the hypotheses we needed to show that many things were preserved when we took limits of functions. So, for example, if I have a sequence of continuous functions which is converging uniformly, then the limit function must also be continuous. So we prove that in 5610. That theorem is not true if you replace uniform convergence with pointwise convergence. Indeed, the example I just mentioned provides a counterexample to that. So uniform convergence, while maybe not as intuitive as pointwise convergence, is sort of the appropriate hypothesis for many of the theorems we need. Okay. Now, we are moving through this relatively quickly because we've already discussed these at length in Math 5610. I would encourage you to go back to those videos if you want a bit more of a refresher about the convergence of those sequences, or sorry, those types of convergence of sequences of functions. But what we want to focus on in this video is how we might either adapt these or develop new ways of talking about convergence, now using what we know about Lebesgue measure. So the first thing I'll point out is that you can essentially adapt both pointwise and uniform convergence by just adding on almost everywhere. So in general, we say that a sequence f sub n converges almost everywhere to f if and only if f sub n converges to f except on a subset D having measure 0. Now, I was sort of intentionally vague here, right? So we could, this really gives rise to two ways of thinking about this. So you can think about pointwise almost everywhere. Okay. And again, we often abbreviate that almost everywhere AE, okay? Or uniform almost everywhere. Now, again, what does this mean? Pointwise almost everywhere simply means that your sequence of functions, it converges pointwise almost everywhere on D, except possibly on some subset of D which has measure 0. Similarly, with uniform convergence, what does uniform convergence mean? It means that my sequence of functions should converge uniformly on D, except possibly on some subset of measure zero. So the idea is you have, sort of this convergence, either pointwise or uniform. And with pointwise, it's particularly easy to sort of think. You go through and for each x value in your domain, right, you sort of check and say, well, does it converge pointwise at this point? So like maybe you check, now there's uncountably infinitely many things here, right? So, you check and sort of say, okay, yes, it converges pointwise at that x value and at that x value and at that x value. And then you go, oh no, it doesn't actually converge pointwise at that x value, but it does at this one and this one and this one and this one. So you go all through your domain sort of checking, at which x values does this converge pointwise. And then at the end, what you do is you look at the measure of this set, so the set of all x, such that if we're doing pointwise convergence, this would be the set of all x such that the limit as n goes to infinity of f sub n of x is not equal to f of x. Okay, so that's again just saying set of all x where the pointwise limit of this either doesn't exist or it exists but is not equal to f of x. If this set has measure 0, then that would imply that f sub n converges to f pointwise almost everywhere. Okay. If this set had any measure other than 0, any positive measure, then it would not converge pointwise almost everywhere. Now, you can again do a similar thing with uniform convergence. Okay, so again, remember the key difference between uniform and pointwise is that for uniform, you want to be able to choose that n that's independent of x. Well, say that you couldn't do that. Okay, you sort of see, well, how many x values can I not do that for, right? If the measure of that set of x values has measure 0, then I could still say it converges uniformly almost everywhere. Now, it actually turns out, so these are sort of natural analogs, right, of pointwise and uniform. So I can think about lying up here, right, there's pointwise convergence, okay? And of course, if something converges pointwise, then it converges pointwise almost everywhere. Why? Well, if it converges pointwise, then what is the set of all x values such that f does not converge pointwise? It's the empty set, right? So the empty set has measure 0. So pointwise convergence implies pointwise almost everywhere convergence. Similarly, uniform convergence implies uniform almost everywhere convergence. Okay. Recall also, right, that uniform convergence implies pointwise convergence, right? Converse is not true, but uniform convergence does imply pointwise convergence, okay? Now, it turns out that pointwise almost everywhere convergence, this is something that actually turns out to be fairly useful. Pointwise and uniform, we've already seen a lot of uses for those. Uniform almost everywhere convergence turns out just not to be quite so useful. And again, we're going to look at an example. I keep sort of teasing this example. It's going to come up after one more definition. But again, it'll sort of help tie together all of these definitions. It actually turns out that this uniform almost everywhere convergence is just not, it's just not quite as useful. But there is another type of uniform convergence that is very similar to uniform almost everywhere, but it's not equivalent, and it's slightly different. Now, the problem is its name sounds very similar to uniform almost everywhere convergence. It's going to be called almost uniform convergence. Okay, again, so we have two different things. We have uniform almost everywhere. That means that the convergence is uniform except on some set of measure 0. And then we're going to have this almost uniform convergence. Now, again, these are very, it's a little bit of unfortunate naming in some ways. They sound so similar, but are actually different. They are, again, I said they're not equivalent, but one of them does imply the other, and we'll actually see in just a moment what that is. But the first thing we need to do is define almost uniform convergence. All right. So we say that a sequence of functions, so assume f sub n is a sequence of functions defined on a measurable set D with finite measure. Then we say that a sequence of functions f sub n converges almost uniformly to a function f on D, if and only if, for every epsilon, there is a measurable set. Now, we're going to call this set E sub epsilon. So notice that the set, as our epsilon changes, this set E sub epsilon is going to change. So that for every epsilon, there is a measurable set E sub epsilon, which is a subset of D, with the measure of E sub epsilon being less than epsilon, such that f sub n converges uniformly to f on D intersect E sub epsilon complement. Now, what is this set? This is the complement of E sub epsilon in D. Okay. Now, let's slow down and try to process this, and then again, we'll use an example to help us really make sense of this. So what this definition is saying is that for every epsilon, I want to be able to show that f sub n converges uniformly to f on some set which is almost D, except I've taken out some set of measure less than epsilon. So basically the idea here is I don't have to, it's not just that I take out some fixed number of points, it's that I take out, or some set of points, and that set has measure 0. That would be uniform almost everywhere. With almost uniform convergence, what I say is, well, for every epsilon, I can go through and I can find some set of points that if I pull that set of points out, it converges on D intersect the complement of that set of points that I pulled out. Okay, so it converges on that set, and that set that I had to pull out, it doesn't have measure 0, but it has measure less than epsilon. Okay, so let's now look at all of these types of convergence. Now, having defined them, let's look at them through the lens of a particular example. And the example I want to use here is this example that I mentioned. So I want to look at f sub n of x is equal to x to the n on the interval 0, 1. Now, let's walk through. Right now, we have 5 types of convergence we've talked about: pointwise, uniform, pointwise almost everywhere, uniform almost everywhere, and almost uniform convergence. All right, so you can see here, so plotted in these sort of varying shades of yellow are the sequence functions. So this is F1, F2, F3, F4, F5, F6. And then the limit function is sort of in green here. So the pointwise limit is 0 everywhere except at 1, where it has the value 1. Okay. So we showed in Math 5610. So if we write out our 5 types of convergence, so we have pointwise almost everywhere. We have uniform almost everywhere. And we have almost uniform. So let's walk through each of these. So in 5610, we showed that this sequence of functions converges pointwise, right? And the idea, right, is just pick any x value you want, right? If you fix this x value and then you look at f1 of x, f2 of x, f3 of x, f4 of x, f5 of x, so on and so on, those values are converging down to 0 for every x between 0 and 1, including 0 but not 1. At 1, every one of these functions has value 1, and so they converge to 1. So again, so these converge pointwise to, and we should just write here, this limit function f, which again is plotted in green over here, which is simply 0 if x is between 0 and 1, including 0 but not 1, and 1 if x is equal to 1. So the sequence of functions certainly converges pointwise to 0, 1, to this function f. Therefore, it converges pointwise almost everywhere. Okay. Now, this sequence of functions does not converge uniformly. Okay. Now, why does this sequence of functions not converge uniformly? Well, fundamentally, the idea is the following. If I look at and sort of imagine, okay, I want to look at f sub n of x minus f of x. Okay. Well, for x in this interval, 0, 1, so if x is in the 0, 1, okay, this difference is just going to be x to the n. Be x to the n minus 0. Now, the question becomes, well, okay, what if I wanted to make this, like I want to make this, say, less than some epsilon, right? That would be my goal. I want to choose a capital N such that this is going to be less than epsilon. So one thing I could do here is I could say, well, I'll just move these inside, and I could just take a natural log of both sides. Okay, so if I want absolute value of x sub n less than epsilon, I take a natural log of both sides. Natural log is monotone, so a monotone function. So I just get natural log of x to the n is less than natural log of epsilon. Now I can bring this n down out front, right? That's a property of natural logs. And then I'll just divide both sides by natural log of x. Because x is smaller than 1, that'll actually be negative. That's going to flip this inequality. So that would imply that little n needs to be greater than natural log of epsilon over natural log of absolute value of x. Okay. Now again, if we imagine we're thinking about small epsilon, right, then this is going to be negative over negative. So this will be positive. Okay. And we get this. Now, the problem here, of course, is normally, like for pointwise convergence, I say, great, there's my capital N. Okay. But for uniform convergence, I need this to be independent of x. Now, a common way you might try to do this is you might try to say, well, let me bound this even further below by asking myself, you know, what's the worst this could be, right? So sorry, not bounding it. What I want to do is I want to bound this expression above. The problem is, as x goes to 1, right? X is never equal to 1, but as x approaches 1, this term is going to 0, which means this thing is blowing up. So there's actually no way to bound this above independent of x. Okay. And so we get pointwise but not uniform convergence here. And you might say, well, okay, let's throw out 1, but notice that the problem isn't at 1, it's just anywhere near 1, right? So the fact that we can't get rid of, like, even if we got rid of 1, this wouldn't work. So it's not even uniform almost everywhere. It's not even like we can just remove 1. We actually would need to delete a whole neighborhood. We need to keep this expression away from 1 at all. Okay. This is where almost uniform convergence comes in. Because almost uniform convergence says, well, I really just need to be able to pick out some set E sub epsilon, and that's going to be the set that I throw away. So for almost uniform convergence, I'm going to select my set E sub epsilon to be the set 1 minus epsilon. Actually, sorry, I need 1 minus epsilon over 2 for a reason we'll see here in a second, up to 1. Okay. Now, why does that help me? Well, for almost uniform convergence, I just need to show that for every epsilon, okay, for every epsilon, there exists this set. Okay, that's a perfectly good set for every epsilon. Okay. Now, notice that if I look back at that definition of almost uniform convergence, right, I need the measure of E sub epsilon, I need it to be less than epsilon. Well, this is an interval. Its measure is just its length. So its measure is exactly epsilon over 2, which is less than epsilon. Okay. And if I look at the set D, that's just my domain, intersect E sub epsilon complement. Well, my domain here is just 0, 1. Intersect the complement of this, I just get 0 up to 1 minus epsilon over 2, not including that. On this set, f sub n of x does converge f sub n does converge uniformly to f. because now if I look at this distance, okay, so I want to make this less than epsilon. I go through the same process, right? So I need this to be less than epsilon. That implies that I need n to be greater than the natural log of epsilon over the natural log of x. But now this absolute value of x, it's bounded away from 1. So this quantity here, right, this is always less than natural log of epsilon over natural log of 1 minus epsilon over 2. And so I can actually choose this as my capital N, that notice this is independent of x. And so on this set, for every epsilon on this set, my sequence of functions is converging uniformly. So the idea is my sequence of functions is converging uniformly on any interval as long as I stop somewhere short of 1. But I can never just get rid of 1. This set that I'm removing, it has positive measure. Right? This is the set I'm removing. It has positive measure. But the idea is it's not enough to just delete 1 here, but as long as I delete any neighborhood of 1, I will get to uniform convergence. So in some ways, the way I think of almost uniform convergence is, okay, it's not going to be enough to just remove these points. If it was enough to just remove, like a finite number of points, then I would say it's uniform almost everywhere. But in this case, it's not enough to do that. I need to not only remove the point, I need to be able to remove some neighborhood. And it turns out that even if you had like countably many of these points, right, and you needed to, as long as you could remove arbitrary neighborhoods around each one, you would still get almost uniform convergence. So we have this other notion of sort of a type of uniform convergence precisely because many times the issue that is happening when you have a sequence of functions that's not converging uniformly, it's not just a problem at the particular point, it's actually a problem in any neighborhood of a point. So almost uniform gives you sort of that flexibility to not just remove the point and say, oh, there's just a small measure set of points where I'm having a problem. It's that I'm having the problems at these points and I need to be able to remove not only those points, but neighborhoods of those. And almost uniform gives you that flexibility, okay? So we can immediately, so here actually we do get almost uniform convergence. Now from this, we can already see that almost uniform does not imply uniform almost everywhere. However, uniform almost everywhere does imply almost uniform, okay? So you actually have this sort of hierarchy for uniform convergence where uniform implies uniform almost everywhere implies almost uniform. But the reverse implications do not follow. Okay. All right. Now, I would describe each of these types of convergence in a way, they're really local forms of convergence, right? So you're looking sort of at x values, and fundamentally, even with uniform convergence, you're really asking, does f sub n of x converge to f of x, right? And yeah, you're wanting it to really, with the difference between uniform and pointwise, has more to do with the rate at which they converge and not the fact that you're looking sort of locally for each x value, is this converging, right? But now with measure, we actually get what I would describe as some more global ways of thinking about convergence. Now, we're going to finish this video by defining them and looking at one example. However, if after watching this video, you still find yourself a little confused, don't worry too much about it. In the next video, we're just going to spend some time looking at more examples. And then in the video following that, once we have those extra examples, what we want to do is then try to understand, how are all these different types of convergence related to each other. So we're going to end up with 2 additional types of convergence. So we've already written 5 up here. We're going to get 2 more. We're going to have 7 types of convergence, and we're going to want to understand which of these imply others. Now, some of these examples will help us rule out certain possibilities, right? So we saw that this converges almost uniformly, but not uniformly almost everywhere. So I know then, just based on this example, that almost uniform convergence cannot imply uniform almost everywhere, right? So some of these examples will help us as we go as well. So let's define two more types of convergence. So the first is what we're going to call convergence in mean. So let f sub n be a sequence of integrable functions defined on a measurable set D. The sequence f sub n converges in mean to a function f on D if and only if the limit as n goes to infinity of the Lebesgue integral of the absolute value of the difference of fn of f and f goes to 0 as n goes to infinity, right? So, and the idea here, and again, why I describe this as more of a global type of convergence, right? The idea is I have some, say, target function f here, and I have the sequence of functions, so maybe like this is f sub n, right? This is one thing in my limit. And let's say I'm working on, say, this set. Say the set D is again just some interval here. So sorry, this whole thing is just my domain D. So what I'm actually going to do is, and as I've drawn these are like nice continuous functions, so they're Riemann integrable. So this Lebesgue integral is really just the Riemann integral. So I just look at sort of the area between these two curves, and the question becomes not anything about whether or not this point is converging to this point, but rather what's happening to this area. Is it going to 0? Okay. Now, you might think, well, doesn't that, I mean, that must imply, right? Like, how could the area go to 0, right, without the function values actually going to 0? We'll actually see that convergence in mean does not imply pointwise convergence. In fact, one of the homework problems actually shows, even though we weren't quite ready for this language yet, and we'll circle back to this in the next video, but it actually shows that convergence in mean does not imply pointwise convergence. Okay. So again, I think of this as a more global type of convergence because it's not focused on any particular x value. It's looking at what's happening over the whole domain D. Okay. Now, again, if you deal with only, say, sequences of continuous functions, then lots of other things become true. So for continuous functions, right, the only way the integrals can go to 0 for continuous functions, right, is if pointwise it goes to 0. But if these are not continuous functions, then you don't have to assume anything like that, right? It's actually possible for integrals to go to 0 without pointwise everything going to 0. So again, we'll see that in the context of an example. Now, the other type of sort of more global notion of convergence is something called convergence in measure. So let f sub n be a sequence of measurable functions defined on a measurable set D. Then we say the sequence f sub n converges in measure to a function f on D, if and only if, for every epsilon, the set of all x values in my domain such that f sub n of x and f of x differ by more than epsilon goes to 0 as n goes to infinity. So sort of said another way, what this is really saying is, as I move further and further out in my sequence of functions, the set of x values where my function differs by more than epsilon from f, the measure of that set ought to be going to 0. Okay. Now, to help us sort of understand both of these, okay, let's again look at an example, and we'll finish the video by looking at this example. Let's think about the sequence of functions g sub n of x is equal to n times the indicator function of the interval 0 to 1 over n. Okay. The first, let's start. I intentionally didn't put a graph up here because I think it's valuable to think about like what's even happening here. Okay. So these functions are defined. I guess I didn't write it here. I'm thinking of these functions as being defined on the interval 0, 1. Okay. This is add up here. This is on 0, 1. Okay. So what is the first function? So the first function, I just sort of write out a couple of them here. So g1 of x This is 1 times the indicator function of 0, 1. Okay. Well, the indicator function 0, 1, it's just 1 when x is in 0, 1. That's the only x values we're working about. This is just a constant function 1. All right. So I'm going to, so again, help with our scale here. All right. So here's G1. What about G2? Well, G2, it's going to be 2 times the indicator function of 0 to 1 over 2, or 1/2 of x. Now, this, when x is between 0 and 1/2, this function is 1. So between 0 and 1/2, this takes the value 2. Okay. But outside of that set, right, the indicator function 0, so outside of that set, this is 0. And so that's G2 in blue here. And now maybe you've started to sort of sense the pattern. Let's maybe write out one more. So G3 of x, right, that's going to be 3 times the indicator function of 0 to 1/3. So between 0 and 1/3, right, my function is going to have a height of 3. But outside of that, it's going to be 0. Okay. So what's happening is sort of you have this function. One way to think of these are like they're almost like rectangles, right? Let's sort of draw these in. These functions are like rectangles, right? But what you're doing is your base is always length 1 over n. Your height is always n. So if, for example, I were to calculate the integral of g sub n of x, or let's say the integral of g sub n d mu over 0, 1. Well, these things are all, they only have 1 point of discontinuity. They're all Riemann integrable. So the Lebesgue integral is equal to the Riemann integral here, right? And the Riemann integral is just going to give you the area under the curve. Well, notice that these are always have value n, but it only has the value n on the interval 1 over n, or 0 to 1 over n. So each of these integrals is 1. Okay. So if I look at this, another way to express this would be to say if I look at the integral over 0 to 1 of g sub n minus 0 d mu, okay, that's just going to be equal to this, right? Because these are equal. Right? G sub n is always positive. Subtracting 0 doesn't change anything. So this is always equal to 1. Right? So what's happening here? Well, I have this sequence of functions, but this integral, like this is not going to 0. Right? So these are not converging in mean. Okay. But we could ask, are they converging in measure? Okay, so this set, if I look in mean, no. Then I ask about, well, what about in measure? Well, if I want to know if this sequence of functions is converging in measure, then what do I want to look at? I want to look at the measure of the set of all x values, in this case in 0, 1, such that such that the difference between, in this case, not f sub n, but g sub n of x, and if I think these are converging to 0, 0 is greater than epsilon. Yeah. So the first question I ask myself is like, okay, well, what even is this set, right? What are the set of x values such that g sub n of x minus 0 is greater than epsilon? Well, if I just look at this set, it's really just the set of all x such that g sub n is greater than epsilon, because this is always positive. Subtracting 0 doesn't do anything. Okay. That's really like asking, where is g sub n not 0, right? So, I mean, I guess it depends also on what your epsilon is. But certainly what you can say is that this is always 0, right? Your g sub n is always 0 on the interval 1 over n to 1, right? So this is always a subset of 0 to 1 over n. Right? The only places where g sub n could be greater than epsilon, right, are where g sub n is non-zero. Because if g sub n is 0 and epsilon has to be greater than 0, then g sub n will never be greater than epsilon. So the only x values where you could possibly have g sub n of x greater than epsilon are the places where g sub n of x is equal to n. Okay. Now, why does that help us? Well, now if I use monotonicity of the measure, that gives me that the measure of this set is a measure is less than or equal to, so because they were subsets of each other, the measure of this set is less than or equal to the measure of this set. And now if I take a limit of both sides, the limit as n goes to infinity of the measure of this set, well, that has to be less than or equal to the limit as n goes to infinity of the measure of this set. The measure of this set, this is an interval, so its measure is 1 over n. The limit as n goes to infinity of 1 over n is just 0. Each of these things is a measure, so they're non-negative, right? The limit of a sequence of non-negative numbers must be non-negative. So this can't possibly be negative, so it must be equal to 0. Okay. And so what we see here, and this sort of gives us a nice example, here what we see is the set on which g sub n is not converging to g is getting smaller and smaller and smaller. The problem is on the set where it's not converging, it's actually like blowing up, right? And so here we sort of we don't get this convergence in mean, but all convergence in measure cares about is sort of, what's happening in terms of like, where is it not converging? Is the set of places where it's not converging getting small enough? And here by not converging, right, we even mean in a fairly weak sense, just what's the measure of the set of x values such that g sub n of x minus g of x is greater than epsilon. All right. Now, again, we are going to spend the entire next video just working through more examples. This video was really meant to introduce you to the definitions and begin to get you thinking about how some of them work, but we will help solidify all of those ideas as well as begin to think about some new ones in the next video.